Year 13 Vectors. Let's start by going back over what we already know about vectors. So we've covered vectors in 2 dimensions before, and there are lots of different ways in which we can express a vector. For instance, I might write a vector like this, R, underlined to show it's a vector, and if it's in a textbook or in print, it will be in bold, it may not be underlined. Now, you should have come across column vectors before, with 2 components, like this. We can also express a vector in its I and j component form. So this column vector xy can also be written as xi plus yj, where we can define I as the unit vector 1, 0, so 1 unit along like that, and j is the unit vector 0, 1, so it's 1 unit upwards like this. We're not using the squares on the page to represent 1 unit here. So what else can we do with vectors? Well, we can work out the magnitude or the modulus of a vector, which means the length of the line representing that vector. So let's take an example and see what we could do with this. I'm going to define the vector r as being the vector 3i plus 4j. Now, what would that vector look like? That's 3 units along and 4 units up. I could write it as a column like this. So, for instance, if I decide that on my scale here, these are the markings on the axes, then if I want to draw this as a vector, I want to go 3 units along, 4 units up, and then if I join up from there to there, I can create my vector r. So if I want to work out the magnitude of this vector, which we write as r modulus, then I need to work out the length of this line, which I can do very easily using Pythagoras' theorem. Here's a right angle triangle, base length 3, height length 4. So it's simply 3 squared plus 4 squared, all square rooted, which of course means the magnitude of the vector, the length of that line, is 5 units. Now we can generalise this. So if my vector has a more general format like this, the magnitude of this vector, which we would write as mod r, would be x squared plus y squared, all square rooted. And it doesn't matter if x and y are negative because we're interested in the magnitude here. Now, what about the direction of my vector? To provide the direction of a vector, I can give an angle or perhaps a bearing. So, for example, let's take the vector 3i plus 4j that we were looking at previously. To provide the direction of this vector, I might calculate this angle here, for example, which I can do very easily using some basic trigonometry. Theta is equal to tan to the minus 1 of 4/3, which works out to be 53.13 degrees. 53.1 degrees to 1 decimal place. If I wanted to, I could work out the bearing by subtracting this angle from 90 degrees. So as long as we're clear about what angle is used to define our vector, we can provide different ways of doing this. So to provide the direction of a vector, we find an appropriate angle or bearing. And in this case, I can say my vector of 3i plus 4j is 53.1 degrees above the horizontal. So we know that vectors are quantities that have magnitude and direction. They can be expressed as columns, they can be expressed in I and j component form, and we know how to calculate the magnitude and provide the direction of a vector. So we're now going to have a look at extending these concepts to 3 dimensions, and I'm going to start by identifying the I and j vectors that we talked about previously in 3 dimensions. So the I vector, we now have to have the vector in 3 parts, 1, 0, 0. The j vector becomes 0, 1, 0. And we have a k vector, which is the vector 0, 0, 1. It can be a little bit tricky to draw this, but let's imagine that our x-axis is along like that, our y-axis is along like that, so those two are perpendicular to each other, and then we have the z-axis, which is perpendicular to both of these. If you imagine you draw the x and y axes on a sheet of paper, the z-axis would then come off that sheet of paper. It would be perpendicular to the sheet of paper. So the I vector lies along the x-axis like that, the j vector lies along the y-axis like that, and the k vector lies along the z-axis like that, and all 3 are mutually perpendicular and they are all unit vectors, i.e. they have a magnitude of 1. So let's suppose we have a vector r. If it's a vector that we're defining in 3 dimensions, it will have 3 components, x, y and z. We can write it in its component form as xi plus yj plus zk. Now we can work out the magnitude of this vector in exactly the same way that we worked out the magnitude of a vector in 2 dimensions. The modulus of r, or the magnitude of r, would simply be x squared plus y squared plus z squared, and we square root all 3 parts of that. You've actually done something very much like this when you studied trigonometry in 3 dimensions back at GCSE. Let's have a look at an example. I'm going to define the vector r as 2i minus 3j minus k. Some people find it difficult to work in component form, in which case write the vector in column form so you can see all 3 components very clearly. Now if I want to work out the magnitude of that vector, I would work out 2 squared, and again this can be -3 or 3, it doesn't really make any difference. There we go, and then square root this, which gives me root 14 in surd form. Now, identifying the direction of a vector in 3 dimensions is more ambiguous and more complex, so this is not something we're going to look at doing at the moment. Now, we've briefly mentioned that the vectors I, j and k now are all unit vectors, so let's go into this in a little bit more detail. A unit vector is a vector that has a magnitude of 1. So the vectors I, j and k are special examples of unit vectors, but they're not the only vectors that are unit. So let's look at an example. We've got to find a unit vector, so a vector of magnitude 1, that is in the same direction as the vector r equals 3i plus 4j. Now, we looked at this vector previously. We know its magnitude is equal to 5. We know that this vector is 3 units along and 4 units up, so it looks a bit like this. I'm not using the squares here to scale, I'm just sketching it out. It's 3 units to the right and 4 units up, so here is my vector r. So what I want to do is find a vector that lies on this line, so is in exactly the same direction as r, but it has a magnitude of 1 rather than the magnitude of 5 which r has. And I call this unit vector r hat, which means it's in exactly the same direction as r, the original vector r, but it has a length of 1. Now hopefully you can see that there's a very simple way to find this vector. We simply take the vector r and divide each part by its magnitude. So r hat would be equal to 1/5 of 3i plus 4j. or 3/5 of I plus 4/5 of j. So we basically scale down this right angle triangle like that. Now let's just double check. If we work out the magnitude of r hat, that's going to be 3/5 squared plus 4/5 squared, square rooted. So that is the square root of 9/25 plus 16/25, which you can work out to be equal to 1. So if we want to work out a unit vector that is in the same direction as another vector r, we simply take that vector r and divide it by its magnitude. And here's this written as a formula. R hat is equal to r divided by mod r. And that's a really useful way of working out a unit vector in a particular direction. So let's suppose we have a pair of vectors. I'm going to call one of the vectors A, and I'm going to call the other vector B. How would we know if the vectors A and B were actually equal to each other? Well, there are two conditions. They would have to have exactly the same magnitude and they would have to have exactly the same direction. So let's suppose I have two vectors. Let's look at an example. I'm going to say my vector A is equal to 4i plus, and then in brackets, 2t minus 3j. So the 2t minus 3 all become part of the j component. And my vector B is equal to 8pi minus 13j. Now, how would I know if these two vectors were equal? How would I know if they had the same magnitude and the same direction? Well, the two vectors can only be equal if their I components and their j components are equal. Now, if this is the case, then this will ensure that the vectors have the same magnitude and the same direction. So let's look at these two vectors in a little bit more detail. So the vector A can be written as a column, 4, 2t minus 3. And if we're saying that this is equal to the vector B, here's B as a column, 8p as its I component, negative 13 as its j component. So this is true if A is equal to B. Now, what does this then tell us? If we look at the I components, we can see that the only way for this to be true is if 4 is equal to 8p, which gives us p is equal to 0.5 or a half. Now, if the j components are equal, then this tells us that 2t minus 3 must be equal to negative 13, which tells us that t is equal to negative 5. So if p equals a half and t equals negative 5, then vectors A and B can be equal to each other or are equal to each other. Another way of phrasing this question might be, if A and B are equal to each other, find the values of t and p, which is what we've done. So let's see what we remember about parallel vectors. I'm going to write down some examples of vectors that are parallel to each other. So the vector 2, 4, the vector 4, 8, the vector negative 1, negative 2, these are all parallel to each other. Let's sketch what these vectors look like. So the first vector is 2 units to the right and 4 units upwards. So again, I'm not using the squares here as scaling, I'm just sketching what each vector looks like. So that might look a little bit like that. This vector here is 4 units along and 8 units up. So we end up with a pair of parallel vectors. They've got the same gradient. 2 units along and 4 units up is the same as 4 units along and 8 units up. They both have a gradient of 2. Now, this last vector represents a movement of 1 unit to the left and 2 units down. So it looks like that, but it's still parallel to the others. It still has a gradient of 2. It's just travelling in the opposite direction. So for vectors to be parallel to each other, they must be multiples of each other. We can see that the second vector, 4, 8, here, is equal to 2 lots of the vector 2, 4, and this vector here we can see is negative a half of the vector 2, 4. So all 3 vectors here can be written as multiples of each other. So parallel vectors are multiples of each other. Let's take a look at an example. I'm going to define a vector A, which is equal to 6, negative lambda and 2. And I'm going to define a vector B, which is equal to 9, 12, mu. I'm using the Greek letters lambda and mu here. So, supposing we are told that A and B are parallel vectors. Our mission is to try and find the values of lambda and mu that would enable vectors A and B to be parallel to each other. So let's go back to this concept of parallel vectors being multiples of each other. So if A and B are parallel, that means that A is equal to k times the vector B, where k is some constant. Now this means that we can write the vector 6 minus lambda 2 is equal to k multiplied by 9, 12 mu. Notice we could have said k times the vector A is equal to the vector B. We would come out with the same answers at the end. Now, if the 2 vectors are equal to each other, then remember that means their I, j and k components must be equal to each other as well. So we can now write 3 equations based on the I, j and k components. I can say that 6 is equal to 9k, negative lambda is equal to 12k, and 2 is equal to mu k. So the first result here quickly gives us the value of k, it's equal to 2/3. This then allows us to work out that lambda is equal to negative 8, and in turn we can rearrange the last equation to find the value of mu, which is equal to 3. I should just add, to avoid any confusion here, the k that we used in this example is not the k vector or a k component or anything like that. It's just a constant that happens to be called k. I could have used the letter m or the letter p or any other letter as well. Let's have a look at another example. So we are told that the vector 4i plus 5j plus m multiplied by bracket 5i minus 3j is in the direction 6i plus 2j. Find the value of m. So let's deconstruct this vector here in a little bit more detail. 4i plus 5j plus 5mi, if we expand the brackets, minus 3mj. So we can combine the I components here and here and almost factorise out the I part. So we've got 4 plus 5mi, and we can do the same here with the j components as well. So we have plus 5 minus 3mj, which makes that vector a little bit clearer. So if this vector is in the direction of this vector here, that means they are parallel to each other, which means they are multiples of each other. So this then tells us that the vector 4 plus 5m, 5 minus 3m, I'm writing the vector as a column vector because I think this is a little bit simpler, is some multiple, which I'll call p, of the vector 6, 2, like that. Now this then allows us to think about the fact that if 2 vectors are equal to each other, their I components must be equal to each other and their j components must be equal to each other. So this allows me to say that 4 plus 5m is equal to 6p, and of course p here is just some kind of constant, some numerical value that we'll end up finding out. 5 minus 3m is equal to 2p, and I have a pair of simultaneous equations. So I'll call this equation 1 and I'll call this equation 2. And what I'm going to do is I'm going to take equation 2 and I'm going to multiply it by 3, which gives me 15 minus 9m is equal to 6p. So I now have original equation 1, 3 lots of equation 2, and they're both equal to 6p. I'll continue up over here, which allows me to say that 4 plus 5m must be equal to 15 subtract 9m, which gives me 14m is equal to 11. So the value of m is equal to 11 over 14. Slightly unpleasant fraction. Now, if I need the value of p, I can then substitute back into either equation 1 or equation 2 to calculate it. I'm not actually asked for the value of p, I only needed to find the value of m, which I've done. Now, when you've looked at the forces and motions topic, you will have talked about resultant forces in quite some detail. So let's spend a little bit of time talking about resultant vectors and what that actually means. So, let's suppose I have some vectors. I'm going to start with case 1, and I'm going to start with a vector which I'll call vector A. Let's draw it like that. So here's my vector A. I'm going to add to A a vector B, which means I'll draw my vector B directly from the end of vector A. I think I'll just have to move that along slightly like that to get a perfect fit. There we have vector B. Now I'm going to include a third vector, and I'm going to add this vector on as well, and this is going to be vector C. So let's include vector C like that. Just adjust it into place. We have it. And there is vector C. Now, if I now draw in a vector that connects the start of vector A with the end of vector C, like that, and please do bear in mind that's meant to be a straight line, then what we have is the resultant of the three vectors A, B, and C. It is the vector sum. So it's vector A, add vector B, add vector C. So this is the resultant of A, B, and C. So for instance, if A, B, and C represent three forces, then the vector A plus B plus C, this resultant, represents the total effect of those three forces. So we might write down the sum of the forces, the resultant force, or sigma F, as we can write, is equal to A plus B plus C. Of course, this is if A, B, and C represent three forces. They may actually represent three displacements, in which case A plus B plus C represents the displacement of the end of the journey relative to the start of the journey. Let's have a look at a slightly different case scenario. So this time I've got a vector A again, which is going to look something like this. I'm going to add on a vector B to the end of it, which is perhaps going to look something like this. Just move it in position so it's directly at the end of vector A. So there's vector B. And this time it turns out that vector C is like this. So vector C is from the end of vector B back to the start. Now, in this case, we can say if we were trying to add vectors A, B, and C together, then we get back to the beginning. So we create the 0 vector. So again, if A, B, and C represented three forces that we were adding together, in this case, we would say that sigma F is equal to 0. The resultant force is equal to 0. So in this situation, if we were dealing with forces and A, B, and C represented three forces, the object in question on which these forces are acting would be in equilibrium. Let's have a look at some examples. Now, for both these examples, we're going to need two forces. Force P, which is equal to 4i minus 2j minus k, and force Q, which is equal to 2i minus j plus 6k, both forces given in vector form. So for part 1, we are going to find the resultant force if P and Q act on an object. Now, to find the resultant force, remember, we're looking for the vector sum of the forces. So we are looking for sigma F, which is force P plus force Q. Now, you can add the forces in their IJK component form. Some people prefer to write them in column format so they don't get themselves confused by the letters involved. Either way, it doesn't really matter. This gives us a column of 6, negative 3, 5, or in component form, 6i minus 3j plus 5k. Let's have a look at example 2. We are told that an object is in equilibrium under these three forces, 2p, mq and bk, where m and b are constants that we are trying to find the value of. So what we know is the sum of 2p, mq and bk must be equal to 0 because the object is in equilibrium. The vector sum of forces must be 0. I'm going to write this out in component form, which I think will be a bit less confusing. So 2 lots of vector p plus m multiplied by vector q plus b multiplied by the vector k, which remember is 0, 0, 1. And this is equal to the 0 vector, which in 3 dimensions is 0, 0, 0. So looking at the I components first of all, we can say that we have 8 plus 2m is equal to 0, which immediately tells us that m is equal to negative 4. Looking at the j components, we can say that negative 4 minus m is equal to 0, which is good because it confirms that m equals negative 4, so we have consistency. And then looking at the k components, we can say negative 2 plus 6m plus b is equal to 0, and from here we can solve to find the value of b. So we have negative 2 minus 24 plus b equals 0, so this will rearrange to give us b equals 26. So we're going to have a look at position vectors now in comparison to direction vectors. We're going to see whether we understand the difference, the subtle difference between these two types of vector. And we're going to start with an example in 2 dimensions. So have a look at the set of axes with points A, B and C plotted. Now, it's really important that we remember that these are coordinates here. They are not vectors. Coordinates simply denote position, whereas vectors denote movement from one point to another point. They tell you how far to move and they tell you in which direction to move using a combination of horizontal and vertical movements, which has the effect of potentially a diagonal movement. So, how do position vectors relate to coordinates? Well, a position vector is a vector that is defined relative to some specific origin or starting point. So if I wanted to give some examples of position vectors, then I might, for instance, look at the vector OA. Now the vector OA starts at the origin O, and it goes up to point A like that. It's a position vector. It's defined relative to the origin O. Now, what is that vector? Well, it's the vector that gets me to the point with coordinates 3, 7 from the origin, which means it must be the vector 3, 7, or if you like, 3i plus 7j in component form. What about the position vector OB? Well, that starts again at the origin, takes me along to point B like that, And we know that B's coordinates are negative 4, 6. So the position vector of point B is negative 4, 6. So there is a strong relationship between coordinates and position vectors relative to the origin. Write down the position vector for point C. Now you should have written down the vector 0, minus 3 or negative 3j. So these are three position vectors. Now, supposing I want to find a reverse vector, what if you were asked to find the vector, we'll do it over here, let's find the vector AO. Well, hopefully you remember from work you've done on vectors previously that the vector AO is the negative of the vector OA. So it would simply be the vector negative 3, negative 7. Similarly, the vector B to O would be negative OB, so it would be the vector 4, negative 6, and so on. So what about if you were asked to find, for instance, the vector AB? What does that mean? Well, you've come across this idea before. Let's draw on the vector AB like that. Now, to get from A to B using existing vectors, we have to go backwards along this path like that, so along the vector AO. And then we have to go forwards along this path here. So that's plus, I think I'll do it in black rather than yellow, that's not very visible, plus the vector OB. So that would be the vector AO, which is negative 3, negative 7, plus the vector OB, which is negative 4, 6. Adding the I components and the j components separately gives us the vector AB, which is negative 7, negative 1. Now, you could, in theory, think of this as the position vector of the point B relative to the point A, or you could just think of it as the vector position of B in relation to A, because position vectors are usually defined relative to some kind of starting point, common starting point of the origin. So what is a direction vector? Well, a direction vector would be, for instance, if I just said, well, here is the vector P and it's equal to 2, 3. Well, all that tells me is that I move 2 units to the right and 3 units up. It doesn't tell me where I start, so it's not relative to a given origin or any kind of starting point. It simply tells me the direction I move in. If I start here, I would have to go 2 along like that, 3 up like that, and there's my vector P. But if I had a totally different starting point like this, then I go 2 along, 3 up, and I end up in a completely different place, but I've still followed the instructions of vector P. So you can see that this is a direction vector because it's simply telling you how far to move and the direction to move, but it's not giving you a starting point, unlike in these examples here. Have a go at finding the following vectors using the system we've looked at. Can you find the vector AC? Can you find the vector CB? See if you can write these down. So you should have found that the vector AC is the vector AO plus the vector OC, which is negative 3, negative 7, plus 0, negative 3, which comes out to negative 3, negative 10. And the vector CB is the vector CO plus the vector OB, which is equal to 0, 3, plus negative 4, 6, which comes to an answer of negative 4, 9. Now, what would you do if you were straight away then asked to write down the vector BC? Well, you should remember that that's the negative of CB. So that's simply equal to 4, 9. And being able to work flexibly and efficiently like this with vectors is really important. So we're now going to extend what we've done to 3 dimensions. Let's consider 3 points, A, B and C. And you can see they've all got an X, a Y and a Z coordinate. So we're going to start with a sketch. Now, how do we sketch 3 points in 3-dimensional space? Well, the answer is we can't. Not in the same way we would work in 2 dimensions. We can't really draw very accurately without a computer 3-dimensional space. So what we're going to do is just place an origin somewhere randomly on our page. Here it is. And I'm going to mark points A, B and C completely at random because I don't know where they are in three-dimensional space. I can't really draw that very easily. If I had a computer, I could map three-dimensional space. I can't do that on a two-dimensional page. So all I'm going to do is say, well, let's imagine point A with coordinates 2, 5, 1 is over here. Let's imagine that point B is over here. And here are its coordinates, and let's imagine that point C is over here. Now, I have absolutely no idea of where the points are in relation to each other. Really, I simply can't visualise that very easily, but it doesn't matter. Because if I am asked to find the vector OA, which if you remember is a position vector, it's the position of A relative to the O, the origin. Now it looks here from my two-dimensional sketch that A is vertically above O. We know it's not, but I can see that the vector OA is simply represented by the coordinates of the point A, which is 2, 5, 1 as a vector. Or, if you like, in component form, 2i plus 5j plus k. Let's write down the vector OB. Well, that would be this vector over here. Again, don't really pay too much attention to the two dimensions. The drawing is just here, as you'll see in a minute, to help you plot pathways. So the vector O to B is -4, 3, -7, or -4i plus 3j minus 7k. And let's finish off with the vector OC, which is -1, 0, 6, or -i plus 6k. Now, what happens if you are asked to find another vector? So I would like you to think about finding the vector BA. And this is where the diagram comes in handy. Let's draw on the vector B to A, like that. So how do I find that vector? Well, I'm starting at B. I've got to go back along to the origin like that, so the vector B to O, and then I've got to go along up to A. So it's BO plus the vector OA. Now, what are these vectors? Well, the vector B to O is simply the negative of vector OB, and the vector OA, well, we've written it down. It's 2, 5, 1. So this is negative OB, which is 4, -3, 7. Add the vector 2, 5, 1, and if we add our I, J and K components separately, this gives us 6, 2, 8 for the vector BA. So having the points drawn on a piece of paper relative to each other just allows us to plot the pathway. It doesn't really tell us exactly where they are. Let's have a go at another one. So I want to, this time, find the vector B to C. So this tells me that I want to start at B and drop down to C like that. So again, I'm going to go along the vector B. I'm going to go along the vector BO like that, along that blue arrow. And then I'm going to add on the vector O to C. So let's fill these in. So the vector BO, we wrote it down a minute ago, it is the vector 4, -3, 7. And the vector OC is -1, 0, 6. Let's add these two vectors together. So this gives us 3, -3, and 11 to finish off. So I want you to now have a go yourself at finding the following vectors as efficiently as possible, please. Find the vector AB, find the vector AC, find the vector CA. So you should have found that the vector AB very easily is the negative of the vector BA, so it's -6, -2, -8. The vector AC is -3, -5, 5, and then the vector CA is simply the negative of that, which is 3, 5, -5.